I remember when I was sitting in my Introduction to Computer Science course, and my professor just introduced me to this idea of recursion. And I was like, what is this sorcery? It didn't make any sense to me. And it wasn't until I taught a data structures course that recursion started to make a lot more sense to me. So in today's video, I really want to focus on why students don't understand recursion. All right, what is it that makes recursion so difficult? So I think it's important to start off with what is recursion. Recursion we can think of as a programming technique in which a method calls itself over and over in order to determine the answer to a subproblem or a smaller problem. And this smaller problem will allow us to build back up to the solution to the larger problem or the problem that we're solving for. Now, oftentimes I like to equate recursion with the Russian doll example that you may have seen before. All right, you start off with this really large Russian doll, and over time it gets smaller and smaller and smaller until you reach the smallest, most basic Russian doll. But you know that each Russian doll is hiding inside of the bigger Russian doll until you get to that last Russian doll. Another great example to think of recursion as is Google search. Anytime you type in recursion on Google, it'll ask you, did you mean recursion? And then you click it again, and then it'll continue to say, did you mean recursion? And you can click it again and again. And even though you spelled recursion correctly, it still asks you, did you mean recursion, to show you the meaning of recursion. You know, you're constantly calling this method, did you mean recursion, over and over and over. So that's a great way to look at recursion. So I think the next thing we should talk about is why we even use recursion. I think a lot of students focus too much on complaining about recursion and focus less on actually understanding where and why we would use it. All right, so I think a great use case for recursion is when you know the answer to the most basic and smallest solution of a problem. So this can technically be like 1 or 0, or if you have a grid, it's the most smallest 1-by-1 grid. And you'll see this often when we solve problems. Another great use case is if you want to exhaust all the possible choices for a given problem. Think about it. Think about a grid, okay? And you have a bunch of paths that you can take from point A to point B in a grid. All right, so how can you make sure that you're taking the best possible path from A to B? Well, you would have to check every choice. And I think recursion is a great way of doing that. And you can also use recursion if you don't want to utilize an additional or global data structure. And this will make more sense when we talk more about data structures later on this channel. But for now, I think it's important to just recognize that recursion can save you a lot of space in terms of allocating another data structure or an array. And last but not least, my favorite one, honestly, it's probably because you just want to flex. I mean, let's be real. If you can write something in 5 lines of code, why would you write it in 10 or 30, right? I mean, we've been taught to make things efficient. Why not? So now really comes the question, why have you been taught it incorrectly? All right, and I think the main reason is because you're too busy thinking of it as a loop rather than an actual method call. And the issue with that is you're thinking of it as an iteration. But the problem with an iteration is that you're not going back to each method call. And this is something called backtracking, which we'll talk about in a second. Another reason is you can't visualize. And what I mean by visualize is you can't visualize the call stack, which is you're not understanding that when you make a method call, there's a brand new state of that method and everything is new. And so this also goes back to that understanding of lack of backtracking, where you may not understand that when you make a method call or when you call another method, you're allocated all these new variables and you can go back after you're done and figure out the solution to your most basic problem. Which finally brings me to my last point. All right, you're not breaking things down as a base case or a recursive step. All right, base case you can think of as the simplest solution to a problem, and a recursive step is all those method calls. I think we should talk about that more in depth. So I think what we really need to focus on is a 3-step plan to solving problems. Why? Because I think it'll be a lot easier and a lot more helpful if students understand a general guideline that they can use to solve recursive problems. So I think the first thing is to identify the goal of the question. This is really simple. You may think that this is not too difficult to understand, but I want to put it in this perspective. When I mean identify the goal of the question, what I really mean is understand what the final solution is. All right, what problem are you trying to solve? It's kind of working backwards, whereas in iteration, you knew what problem you were trying to solve. Here, you're trying to find the solution so you can figure out how to get to that solution. All right. Whereas before you were solving a problem more, now you're kind of using a solution to solve the problem. You're kind of working backwards. So understanding what the final solution is will help you identify the goal of the question and solve the problem. A base case, well, we talked about this earlier, but base case is the most basic solution to your problem. All right, so that can be either something like 0 or 1 or a 1x1 grid, something along the lines of that. It really depends on what the problem is asking you. It could even be an empty string. Empty string. All right. And last but not least, we should talk about the recursive step. All right. The recursive step has 2 parts to it. The first part is making a call to the same method with different parameters. Now, why do you want different parameters? Well, your goal is to eventually stop this recursive call, I would hope. You don't want that infinite recursive loop like you saw with the "Did you mean recursion" on the google.com search. Rather, you want to make a call to the same method with different parameters, but why? You want to do it so you can make your problem smaller. So your goal is to use different parameters to over time make your problem smaller. All right, so you start off with this really big problem like n, and you want to reduce it down to that 0 or 1. And why? You want to reduce it down to 0 or 1 because that's your base case. You know the answer to that because that's the most basic solution to your problem. And so the recursive step is always going to try to make the problem smaller and smaller so you can eventually reach the goal. So I think it's worth talking about an example. I think examples really help seal your understanding of recursion. So let's talk about factorial. Factorial is a way to represent the product of the current integer and all positive integers less than it until 0. All right, so the factorial of the first 5 integers starting from 0 can be written as follows. So this would be 0 factorial, and we'll get into why soon. This would be 1 factorial. This is 2 factorial, 3 factorial, and 4 factorial. And we can see 4 factorial is represented by 4 times 3 times 2 times 1. Right? And we know that the answer to that is 24. So our goal is to write a problem that uses recursion to solve for n. Before we get started, let's look at another example. So let's look at the example of n equals 5. Right? If you wanted to find factorial of n equals 5, how would you do it? Well, you could do 5 times 4 times 3 times 2 times 1. All right, and you get 5 times 4, which is 20, 20 times 3, which is 60, and 60 times 2, which is 120. Usually I'm bad at math. I'm actually pretty proud of myself for being able to solve that quickly. So that's an example of another factorial. So let's talk about what we understand or know so far. Well, as described earlier, we know that 4 factorial would be something like 4 times 3 times 2 times 1, but also if we look back at the previous slide, we said it's all positive integers less than it until we reach 0. Okay, so what happens if we try to multiply by 0? Well, wait, if you multiply anything by 0, it would equal 0. So that's why when it comes to factorial, even though we include 0, we actually change the value of 0 to 1. So we can say manually change the value of 0 to 1. So that means that if n is ever equal to 0, we know that the answer to that is 1. Okay, if n is ever equal to 0, the answer to that is 1. So we can say that 0 factorial, that's what we know for sure. We know that that's 1. What else do we know? Well, we know that we said 4 factorial is equal to 4 times 3 times 2 times 1 times 1. Well, what's 3 factorial? 3 factorial is equal to 3 times 2 times 1. Wait a second. Let me change colors here to show you what's going on. We see that 3 times 2 times 1 is inside of 4 factorial. So what that means is we could technically change this around and we could say 4 factorial is equal to 4 times 3 factorial. It's the same thing, right? And we can say 3 factorial is the same thing as 3 times 2 factorial. Why? Because we know that 2 factorial is just equal to 2 times 1. And 2 times 1 is inside of 3 factorial. So we can simplify these and make them smaller. And I've now made the problem smaller and smaller. So what we can say is that each time what we're looking for is the answer to n times n minus 1 factorial, right? So that's what we understand so far. Let's move on to the next step. The next step, I would say, is understanding your base case and recursive step, all right? In the previous problem, we identified that we know that if n is equal to 0, that we have 1. We know this for sure. We could also technically say if n is equal to 1, it's 1, and that's totally fine. I just like to keep it as 0, just keep it more mathematically correct. But it's fine either way, whatever you want to do it as. So we can say if n is equal to 0, you know that you have to return 1. All right? Next thing we need to talk about is our recursive step. So in the previous problem, in the previous slide, we talked about 4 factorial equaling 4 times 3 times 2 times 1. All right, well, we know that, and we said we could simplify this by saying 4 factorial is really just 4 times 3 factorial. So then that means that if I wanted to make the problem smaller and smaller each time, which is the goal of our recursive step until we reach our base case, that means that what I really need to do is call the method again on factorial of 3. And then for factorial of 3, I need to call the method again on factorial of 2. And then on factorial of 2, I need to call the method again on factorial of 1. And then on factorial of 1, I need to call the method again on factorial of 0. But we know that the answer to this is 1 based on our base case. So what does that make our recursive step? Well, we know each time we're making the problem smaller and smaller by finding the factorial of n minus 1 until we reach n equals 0. So we can say return factorial of n minus 1 times n, right? So we're multiplying n, which is the current number, by factorial of n minus 1, which is us making the problem smaller and smaller until we reach our base case. I think it's worth visualizing this because I think a lot of students get carried away with this recursive step, but they don't actually understand what's going on because they don't understand how it actually all plays out. So let's draw little boxes. I typically like to use boxes to illustrate my recursive calls. So we could say in this box we have factorial, I'm going to abbreviate here, of 4. And we know that if we want to find the answer to factorial of 4, we need to find 4 times 3 factorial. All right? And so we need to make a call in this method, in this state of the program where factorial of 4 was called, to factorial of 3. All right, so now I've made a call to factorial of 3. In order to solve for factorial of 3, I need to do 3 times factorial of 2, right? So I need to make a recursive call to factorial of 2 because I need to know the answer to that. That's what I'm looking for. So at factorial of 2, I need to find the answer to factorial of 1. All right, and if I want to find the answer to the factorial of 1 in that method call, then I need to make another recursive call to factorial of 1. So we can say 1 is equal to 1 times 0 factorial. Okay, so we can make another call to factorial of 0 because I need to know the answer to that. All right, so we can say factorial of 0, and we know that 0 factorial is equal to 1 based on our base case. And so what do we do in our base case? Well, in our base case, we said if n is equal to 0, we're going to return 1. Well, what happens when we return? Let's actually change colors here to make it a little more descriptive. We do something called backtracking. And what backtracking allows you to do is it allows you to pass that value of 1 to your previous method. So what we're doing is we're passing 1 over to the previous recursive call. And where is that going to land us? Well, if we have factorial of n minus 1 as our recursive call, then that means it'll land right there. That means that in place of factorial of n minus 1, you're not going to have a value of 1 because your base case returned 1 from the previous recursive call. So now 1 was returned, and you can say 0 factorial is 1. All right, now we can do 1 times 1, and 1 times 1 is 1. And if we look at the previous page, if we do that, we're going to return that 1 times 1. And now that 1 times 1 is going to go to the previous recursive call at factorial of 2. At factorial of 2, it's looking for the answer to 1 factorial, so you have 1, and now you can multiply those out. And you get 2 times 1, which is equal to 2. And then you're going to pass that back. Why? Well, once again, you're returning the result. And by returning, you're going to allow it to be passed to the previous recursive call. Because remember, when you return from a method, it returns a result, and it allows you to use that result. So now what we can do is we can replace 2 factorial with 2, and we have 3 times 2, which is going to equal to 6. All right, we can pass 6 back to our original problem. 3 factorial becomes 6, and now you have 24. And there you go. That's how you would solve factorial using recursion. I think it's worth putting this all together in code, so we could say in Java public int factorial, and the first thing you need to do is pass in a parameter of int n, and that's going to be your starting value. Our goal is to reach our base case, so that should be our first piece of code. We can say if n is equal to 0, return 1. Right? Else, we could say return factorial of n minus 1. Remember us making the problem smaller in that recursive step, and multiply it by that current value of n. Right? And that's our code. So I think it's worth looking at this over if it didn't make any sense. But before we wrap this video up, I'd like to take a look at another classic example of recursion, and that's the Fibonacci sequence. Now the Fibonacci sequence we can think of as a series of numbers in which each number in the series is a result of the addition of the previous 2 numbers. And so it can be written as follows. It starts off at 0 because that's what n equals -1 just so happens to be. But we're just going to say it starts off at 1. So we're going to say n is equal to 1 and n is equal to 0 is defined by 1. If you add 1 plus 1 together, you get 2. All right? If you add 1 plus 2 together, you get 3. And if you add 2 plus 3 together, you get 5. So on and so forth until you get the answer to the final solution, which could be whatever n you're looking for, the nth number in the Fibonacci sequence. So if our goal is to write a program that uses recursion to solve the nth Fibonacci number, let's take a look at an example of what that means. So we can say example, if n is equal to 5, we know that that's going to be the answer to what? Well, we know that Fibonacci is the answer, it is the addition of the previous 2 numbers. So what we need to do is we need to look at, in order to solve for this, we can say Fibonacci of n is equal to fib of n minus 1 plus fib of n minus 2. All right, fib of n minus 1, that's going to be, in this case, fib of 4. And this is going to be fib of 3, because we're solving for fib of 5. And the result of that, well, what's fib of 4? Well, we know that over here is 0. We know that this is 0. We know that this is 1, 2, 3, 4. We know that fib of 4 is 5, and fib of 3 is 3. So we know the answer is 8. All right. So what do we know so far? Well, we know that n is equal to 0 is going to return 1. and we know that n is equal to 1 is going to return 1. How do we know this? The problem tells us. It tells us that the first two Fibonacci numbers are 1 and 1. It's kind of the same case as factorial, where 0 just so happens to translate to 1. All right, what else do we know? Well, we know that n is equal to 2 is going to be the result of the addition of the previous two numbers. So 1 plus 1 is equal to 2, right? We weren't able to do that for any other case because n is equal to 1 had n is equal to 0 and n is equal to negative 1 as its two previous numbers, and so we're only going to define it as positive integers. So now n is equal to 3. n is equal to 3 is going to be the addition of the previous two, which is 2 plus 1, which is 3. All right, and then n is equal to 4. n is equal to 4 is going to be 3 plus 2. All right, and then so on and so forth. And you can see this pattern developing. And the pattern that you might be noticing is that you need the answer to the previous two in order to solve for the current, right? So if I need the answer to n is equal to 3 and n equals to 4 to solve for the current, then that's a perfect use case of recursion, because I need to make the problem smaller and smaller until I reach a basic solution, which we know this is our basic solution. And using this basic solution, we'll eventually be able to solve for the larger problem, because we know that n is equal to 0 and n is equal to 1 gives us 1. So let's talk about our base case and recursive step. Well, our base case would be if n is equal to 0 or n is equal to 1, we can return 1. Why? Remember, our base case is the most simplest solution to our problem, and this is given to us, so it's kind of the problem, or it's kind of the solution that we are given. Now we need to talk about our recursive step. So we talked about earlier how fib of n is equal to fib of n minus 1 plus fib of n minus 2. Well, if we know this, then what we know for sure is that each time I'm making the problem smaller and smaller, so the subproblem that I'm trying to solve for is fib of n minus 1 and fib of n minus 2. So it seems like I'm trying to make almost two recursive calls here. If I start off at n, I need to make a recursive call. When it comes to fib of n minus 1, I need to make a recursive call to fib of n minus 2 plus fib of n minus 3. And when it comes to fib of n minus 2, I need to make a call to fib of n minus 3 plus fib of n minus 4. All right? So you continue to do this over and over. And so I think it's obvious at this point that our recursive step is us just going to be returning fib of n minus 1 plus fib of n minus 2. These are the problems we're trying to solve. That's how we're trying to make the problem smaller and smaller. If that didn't make sense to you, let's take a look. So let's just say we start off at fib of 4. All right? This time we have two recursive calls. So I'm going to use sort of a tree. Before I use that little box rectangle method, this time I'm going to use a tree. So we can say fib of 4. Fib of 4 has two such problems it's trying to solve for. And that's fib of 3 and fib of 2. Fib of n minus 1 and fib of n minus 2. All right, well, we don't know the answer to 3 or 2, but we do know that fib of 3 is equal to fib of 2 and fib of 1. And fib of 2 is going to equal to fib of 1 and fib of 0. Well, there's a ding, ding, ding for you, because we know the answer to fib of 1 and fib of 0. But let's finish drawing out this tree before we get too excited. So we can say fib of 2, well, we need the answer to fib of 1 and fib of 0. All right? So let's try to do our backtracking now. So we can say fib of 1, well, we know the answer to that, that's 1, so our method should return 1. It's going to pass 1 back up to the previous recursive call. And then fib of 0, that's going to equal to 1, so it's going to pass 1 up to the fib of 2 recursive call. So now we know that 1 plus 1 is equal to 2. Now 2 is going to be passed up to fib of 3, and we already know the answer to fib of 1 from earlier. We defined that as our base case, that's going to be 1, so now we know that fib of 3 is 2 plus 1, which is equal to 3. Fib of 1 is once again 1, and fib of 0 is once again 1. So we're going to pass both of those up. And now we get 1 plus 1, which is equal to 2. Now we're left with our two final backtracks where we pass these two values up to fib of 4. And fib of 4 is going to hit the nail on this and say 3 plus 2 is equal to 5. All right? If we were to just write out the code, we can say public int fib. I'm going to shorten this because I don't know how to spell. We can say int n. That's our starting parameter. And we can use our base case of if n is equal to 1 or n is equal to 0, we're going to simply return 1. All right? Else, you might just want to return fib of n minus 1 plus fib of n minus 2. All right? So that's how you would solve this using recursion. So what are the takeaways? I would say at the end of the day, your takeaways are understand the problem and establish the goal, which is part 1 of our 3-step plan. You want to visualize the call stack and use backtracking. I showed you 2 ways to do this. One was with a rectangular method and one was with a tree method. You can use either approach. Typically, I use the tree method when there's 2 or more recursive calls, and I use the box method when it's only 1 recursive call. And last but not least, you want to determine the base case and recursive steps each time before you even go ahead and write out the code. So, if there's anything else you need to take away from this that's not included on this list, don't forget that recursion is just a flex. If you enjoyed this video, feel free to subscribe to CSTA, where you can find more tutorials on data structures and algorithms. Leave a like down below if you enjoyed the video, and comment if you have any feedback or want to see other future videos of similar content. I'll catch you in the next one.